Hello students, welcome back to our online session. In today's session of digital signal processing and application class, we are proceeding with the concept of analyzing the functions by using its processing functionality. So let us see with that what else we have covered in the previous session. So we talk about the architecture of your digital signal processor. We talk about the analysis of Fourier transform. We talk about the butterfly diagram for radix 2, 8 points for radix 2, 4 points for radix 2, 2 points by considering DITFFT and DIFFT. So these concepts we covered in the previous session. In the today's session, the main concept of us is to get the analysis part. How do we get that, and what are the important part we are going to consider in our signal processing? That is also we are going to learn in today's session. So before proceeding today's session, students, so we need to understand the previous session's importance of that, and we need to understand the particles, how the things can be designed for using that particular analysis. So just want to see that particular part of it. So let us move ahead with that particular discussion, students. So let us see how we actually, what are the things we have covered in the previous session. In the previous session, we have seen about decimation in time, fast Fourier transform, decimation in frequency, fast Fourier transform for DFT and for IDFT. So both the concepts we have covered. So let us see what else is there for us to discuss in today's session. In today's session, I am just going to talk about FIR filtering and IIR filtering. What is FIR stands for? Finite impulse response filter, and IR stands for infinite impulse response filter. So both the filters we are going to see. We are going to analyze both the parts. We are going to see where actually these filters are using. So basically, we are going to see first method is for IIR. What is IIR stands for? Infinite impulse response. We are going to use an analog filter and digital filter. So what is the meaning of analog filter, students? A filter which are in continuous form, that is considered to be the analog filter. What about digital form? A digital filter is said to be numbers of ones and zeros, so combinations of ones and zeros. If you want to see that one, how it is going to proceed, that particular part is considered to be the digital filter. So now we are just proceeding with analog and digital filter analysis part. So digital filters we are designing by using our windowing techniques. For analog we are using the approximation methods. So now students, so we see that particular part, how it's working. After knowing the working, we can able to proceed with their IIR filtering. So IIR filtering we can understand by considering this analysis part. So with that, we are proceeding with the concept, students. So need to understand how it is going to work. So that working, we can get it by considering its functionality. So basically, we are going to see in that there are two types of approximation techniques are there, students. So one is the Butterworth approximation, second is a Chebyshev approximation. Both are used for approximating techniques. The techniques can be used for applying the analysis part. Whatever the analysis we do have, that analysis we can design by taking this working on it. So whenever we do have any work, students, that can be taken and that can be worked based upon their architecture. So that architecture we can design by considering the IIR filtering. The IIR filtering must be designed and it must be worked based upon its nature. So the nature of that particular two filters are analog in nature. So whatever the analog to digital, if you want to convert, we have to use a technique for that. The techniques we are using, and we are going to discuss that particular technique in today's session. So see here, students, we talk about the filters. In that we learn about low pass, high pass, band pass, even the band stop, right? So band stop means, what is the meaning of band stop? So here only I have stopped in the previous lecture. In today's lecture we are going to learn about band stop filter. So band stop means it resists a particular band of it, and later on it allow the remaining part of the bands. So when we do have such kind of filtering, when I am stopping a specific band and I am allowing other bands to pass. So as you can see in this particular filtering, we do have a specific band has been stopped. That particular part is considered to be the band stop filter, or band stop filter. One more name for that is band reject filter. So rejection in the sense we are rejecting a band. A stop band should be more as compared to the pass band. So whenever we do have this kind of band phenomena, then it's considered to be the band stop filter. So what is a multi-pass filter, students? So multi-pass, students, means a multi-pass filter begins with stop band followed by more than one pass band. That means if you can see the comparison between the pass band and stop band, the pass band needs to be more, so as to pass more number of filtration, so as to pass the more number of information, and the filtration needs to be less. A multi-pass filter in digital filters designers consist of 3 pass bands and 4 stop bands. So in this specific type of thing, the designer default kind of thing. When we see the digital filter designers, they are actually taking 3 pass bands and taking the 4 stop band. The frequencies of that input signals at stop bands are attenuated. So where it is getting attenuation, because obviously it should be done at the stop band only, and whereas the pass bands should allow their particular number of components of frequencies. If they are doing such kind of phenomena, then we can consider to be the multi pass band filters. Next, if you take a vice versa for that, then it needs to be multi stop band filters. What is a multi stop band filter? Multi stop band filters start with pass band followed by more or one stop band. By considering this kind of thing, we can say that it is a multi stop. So here in that all pass filters, an all pass filter is defined as a system that has a constant magnitude response for all frequencies. If you consider any kind of frequency, if irrespective of that particular frequency value, the magnitude response of that filter needs to be constant. So in ideally we can write as h of omega of modulus should be equals to 1. In that kind of scenario, if you're getting a filters, then we can say it is a all pass. It allows all kind of bands to get passed through it. The simplest example for an all pass filter is pure delay system with system function h of z is equals to z power minus k. This is a low pass filter that has a linear phase characteristics. All pass filters find applications such as phase equalizers when placed is cascaded form with the system that has undesired phase response. A phase equalizer is to design compensate for poor phase characteristics of the system. Therefore, it needs to be designed in such a way that if you do have any kind of filtering, that can be analyzed or eradicate the information based upon the filtering. That can be done by all pass filters. So that's the thing we are using it in the digital signal processing application analysis. So here the example for this all pass filter, students, that actually we are using in our control system. So basically when we do have open loop control system or closed loop control systems, in open loop we won't take any feedback, whereas in closed loop control system we use the we use the feedback system. So when we talk about any filtration process, in that if you want to design a particular filter, when I want to attenuate a specific kind of domain filters, when I have to design such type of filters, then that can be designed by applying the all pass filtration. Clear? So these type of filters we need to consider when we are designing the IAR filtration, that is impulse invariant response filtration. So that's the reason we need to go ahead in detail about that. Let's proceed with the other concepts which are related to us. Ideally, how the filters needs to be, that we will see now. So here the ideal characteristics of the filtration that can be understood and designed by considering the 3 parameters. Basic parameters for designing filtration, students, that depends upon 3 parts. One is the gain factor, another is the poles and zeros in the pass band and stop band. Next is their analysis by using magnitude characteristics and the phasor form. So by using these all kind of parameters, I need to assume that filter needs to be what actually in ideally. So basically, if you had an ideal filter, that should be always constant gain. Means if you talk about gain of the filter, what is the use of the gain actually? Gain will talk about how the filtration can be designed. If you see the gain of that particular filter, that must be usually constant. Constant means must be equals to 1. If it is getting that kind of thing, then we can say that the filter is a constant part. Whereas the second point, ideal filters has a linear phasor characteristic. Means there should not be a fluctuation in the response. That should be a constant and it needs to be linear. If you are getting that, then we can say it has a specific linear phase characteristics within their pass band. Third point, students, ideal filters also have constant magnitude characteristics. If you talk about their characteristics response, that needs to be ideal. Then the fourth point is ideal filters are physically unrealizable. Means if you want to see that physical nature, we could not realize their functions. It should not get that any response, or if you apply any transform, the answer should not be specific. The answer should not be the same one if you apply for different responses. Obviously it can't be the same, right? When we apply Z transform, the answer might be different. When you apply any other kind of response, the answer varies. So if you are getting that kind of realization function, then we can say that the ideal filters must be unrealizable. So now, type of digital filters. So these all, whatever we have seen, those are the filters which we are using. Now we are going to see type of digital filters. So it's very important for getting for 10 marks or 5 marks as well. 5 marks mostly it will give difference between FIR filters and IIR filters. For you for the 6th semester for electronics and communication, that's the important answer So note it down and try to maintain the notes for that one also. Try to make the running notes on that. So the point in this is FIR filtration and IR filtration. What is FIR stands for? Finite impulse response. IR stands for infinite impulse response, which is what invariance also we will say. This is called the FIR. IIR is invariant. FIR is variant also. So this is what FIR stands for, finite impulse response. IR is what? Infinite impulse response. So what is a FIR systems? It is a finite duration, whereas IR filtration is infinite duration. Finite means it could be, we know the lower limits and we know the upper limits. If we know both the limits, then we can say it's a finite response. What is IR then? IR is what? Infinite impulse response for that particular filtration. So the second point for that would be h of, for the first point, h of n is equal to 0 for n less than 0 and n greater than or equals to m. That is what m we are considering number of samples for that. Thus the unit samples response exists for the duration from 0 to m minus 1. See, the lower limit is also known and upper limit is also known. That is what it is called finite. Whereas in this same response, but here what is the limit here? 0 to infinity. We don't know about the upper limit, we know about 0, the lower limit, right? So this is called infinite impulse response digital filters. What is FIR? FIR is non-recursive. Means the once it get the answer, it cannot get the repeated answer. We cannot get it from that. That's what it is called as non-recursive. The output of FIR filter depends upon present and past inputs. For FIR, present input as well as the past input is essential. Whereas for IAR systems, it is recursive. Recursive means repetition. Because here we are adding the feedback. So FIR we can assume as open loop system. IAR we can see as closed loop systems. So closed loop means that would be a closed part where you had a feedback in that. So whatever output you get, again it will be feedback. That's what it is. Feedback is there. That is called recursive. It depends upon present input, past input as well as the past outputs. So present, past input as well as the past output. If any system is considered, that is considered to be the IAR. Here as you can see, difference equations of linear system of that particular systems can be assumed as y of n is equals to k is equals to 0 to m summation k is equals to 0 to m bk x of n minus k. So see here only value starting from 0 to m, whereas in this we are taking the previous value, previous output as well as the previous input. See, n minus k is the output, right? Y of n minus k is the past output, x of n minus k is the past input. So any system, if depends upon the past input as well as the past output, that system is considered to be the IIR filtered system. FIR systems has limited or finite memory because obviously when we are saying that it restricts it to particular value only, that's the reason the memory capacity is in MBs only, specific MB or specific GB. It cannot be further added in that. Whereas in IR systems requires infinite memory because it can have a space needs to be more in that. FIR required less number of stages because it know the lower value as well as the higher value. In FIR filters that always are stable because we can say that the systems can use a small duration of analysis. That's the reason it is stable. Whereas IR systems are obviously when it required more number of samples, it will be not guaranteed that the stability must be there. FIR systems and FIR filters can have exactly linear phase response so that there is no phase distortion is occurring with the signal, whereas in IAR it is usually more efficient in designing in terms of computation in time and memory requirements, whereas in IR systems that main concept here is required less processing time because we are taking the storage capacity. When we compare with the FIR filters, it required less number of computation required for it, so that's what the processing time is less. Whereas in FIR filter students, FIR required more number of computation, and that's the reason here the kind of comparison is there. The less requirement of processing time is there in IR filtration when compared to the FIR filtration. Next part, the 7th point. The effect of using finite word length to implement filter, noise and quantization errors are less severe in FIR. So since we use finite word length FWL in order to implement the filtration, so we use this effect. Because of that, the noise and quantization errors are less when compared to the IIR. Whereas since the analogy of filters can be easily and readily transformed into equivalent of IIR digital filters, because of that it cannot be the same, not possible in FIR because that has no analogy counterparts, because we are not using the past inputs and past outputs. Because of that, it should not produce that much of sampling rate easily. So because of that reason, we can say that IIR filtration is not that much efficient enough when compared to the FIR filtration process. Clear? So because of that point, we are assuming in this. So all zeros filters. Here zeros and poles we'll see, as we can see the poles and zeros. Here only we are seeing the zeros. Whereas in IIR filtration, the poles as well as zeros are present because we are considering the past input, past output as well as the present input. So because of these all kind of parameters, poles and zeros both must be present in IIR filtration. Whereas in FIR filtrations, only the zeros are present. Zeros means only numerators are there. There is no denominator part. Because numerator we consider as poles, right? Sorry, numerator is considered as zeros and the denominator is considered as poles. Then FIR filters are generally used if there is no phase distortion. If there is no phase distortion, that particular time only we are using the FIR filtration. If there is a distortion, and the filtration analysis, if you want to see that for FIR, there is no distortion is desired, whereas in IAR, they are generally used if the sharp cutoff and high throughput is required. Because of that, as you can see in the diagram only, in the system describe equation, y of n is equals to y of n minus 1 plus x of n, right? So this is what actually what you can see in this. You can see that there is a past input is also there is a previous input is. So in this, y of n is equals to 0.5 x of n plus 0.5 x of n minus 1. Only the present input and the past input you can assume. If they ask in the question, describe the system whether it is FIR or IR, you can say that when only the inputs, present input or past input, if any system depends, any filtration system depends, then it is what FIR filtration. Whereas any system that depends upon past input, present input as well as the past output, then it is what IAR filtration, right? So the another example for that will be is like 0.5, 0.5 here. The functions will be there, a power n u of n. What is impulse response of that? If you want to see that, also considered to be the what? That's the IAR filtration. Now, how do we design the structures for the FIR systems? So there are the various methods when we can assume for that to design their filtration methods like structures for FIR systems. They are direct form structures, cascaded form structures, frequency sample structures, and lattice structures. By considering these structures, we can design and we can able to find out their structures for FIR systems. So that FIR systems, as you can see for direct form structures, as you can see here in the direct form, what actually we're using? We're using the impulse response, z power minus 1, z power minus 1, so on till infinity. What we are adding? We are adding the plus sign. Plus is nothing but summary. Input, what I am giving x of n, this is my impulse response, right? H of 0, h of 0, h of 1, h of 2, h of 3, so on, h of m minus 1. If I want to go for direct form means only I am directly adding all the numbers, then this is called it as direct form realization of FIR system. Because FIR system depends upon the present inputs, past inputs as well as the past outputs. That's the reason it is what in this way we can write. So direct form of realization we have mentioned as y of n for FIR filtration. K is equals to 0 to m minus 1, h of k, x of n minus k, right? H of k is what? Impulse response. If you want to substitute the values of k differently, like put k is equals to 0. So h of 0, put 0 here. What will get? K 0 means x of n plus h of 1, x of n minus k. So on till last is wherever k is the right, m minus 1, m minus 1, n minus m minus 1. So minus to minus plus. So minus n minus m plus 1 you will get. So this is what actually, this is the above equation we can realize. So this above equation how I am writing in the structured form. So as you can see, first there is no z time. Z when it come into picture when we do have any input value. This is x of n. Whatever we had, we have to multiply with z power minus 1 so that it will become x of n minus 1. If you multiply for one more time, then it will become x of n minus 2. If you multiply one more time, x of n minus 3. So on, if you multiply with x of n minus 1 plus 1 time, it will be same way. Right? Why I am writing z power minus 1? So as to get this minus terms. I need to add these two, right? I need to multiply these two, h of 0 into x of n. If I multiply, I got the first point here. Right? If I multiply with the second, x of n minus 1 into h of n, I'll get the second one. Why I am adding plus sign? Because I want to add these two terms, right? So I need to add that. That's the reason I am mentioning this structure. Likewise, I can apply for so on till infinity. So this is what? Direct form of realization of FIR systems. So what are the things we have to see in that? So there are m minus 1 unity delayed blocks are there. See how many block delays? M minus 1, because at the end we are taking m minus 1 only, right? Upper limit is what? Finite. And 1 unit delay blocks required 1 memory. For each block there should be 1 memory. Location needs to be assigned. Without that it will be merged. If we don't want to merge the memory location, if it merged, there is no information. It has to be specific memory location for all the blocks. That's the reason direct form of structure requires m minus 1 memory locations, and the multiplication of h of k into x of n minus k is performed with the values from 0 to m minus 1. M multiplication and m minus 1 additions are required for that blocks. So that's the reason these are the steps we need to consider for direct form of structures is often called as transfer or tap delay line of filtration. That's the reason it is called as that particular form also. That's it for today's session, students. So in the next sessions, we are going to see how it is going to work and what are the things it's going to analyze and functionality of it. So what we have learned in today's session, we have seen the structure of FIR systems, we have seen the difference of FIR and IR, and we have seen the different types of analog filters, starting from low pass, high pass, band pass, band stop, all pass, and all stop. Right? The multi-pass filter, multi-stop filter, and all-pass filter. These are the 7 types of filters. So you need to learn for analyzing the particular filtration for IAR. It is used for actually Butterworth and Chebyshev approximation. We are going to use that.